actually, just for proper normalization, I should put a 1/2 here, because I'm symmetrizing it. So let's see, if we expect that anything that we will write down will already respect these two symmetry generate. Oh, sorry. Okay, let me just put it a little bit up here. So we expect that anything that we write down should respect both translation and Lorentz rotation. Now, I already mentioned before that this will obviously, once I write it in terms of angle and square bracket, it's already Lorentz invariance, but you can explicitly see why now, because notice that the Lorentz generators are basically derivatives, and they're exchanging the alpha and beta, but they're exchanging the symmetric part of alpha beta. But here, the alpha and beta here in the angle bracket, or the alpha dot and beta in the square bracket, they're antisymmetric because they're contracted with the Levi-Civita. So this doesn't do anything when it acts on the angle and the square bracket. Okay, so it's trivially satisfied that it is Lorentz invariance. Now, momentum translation invariance is slightly non-trivial, and actually, during the course of this lecture, you'll see that how to solve momentum conservation, the different ways of solving it, actually gives you a very interesting insights into the structure of amplitudes. But we won't go into that now, but we're just going to solve this condition in the most trivial way, because the Lorentz invariance, the translation symmetry generator is just a multiplicative generator, right? It's just a product of two spinors multiplying your function. So the only way that a multiplicative thing multiplying your function is 0 is if your function is proportional to the delta function of it. Okay, so this is basically a reflection that we usually, when we write down our amplitude, we actually implicitly have the overall momentum delta function times 1. Okay, we have it has a support on when all the momentum are sums up to 0. Okay, once I write it at this form, then it's obvious that p multiplied by delta p is 0. Right? Okay, it's just x times delta x is 0. Okay, but this tells you a very important lesson, because we're going to use it in just a few seconds, is that anytime you have a generator that is multiplicative, the way to solve that, the constraint that is imposed by that generator, is to have your function to be proportional to that generator as a delta function. Okay, good. So we have Poincare symmetry. Now we're going to enlarge our symmetry. So how can we enlarge our symmetry? Well, of course, there's a lot of ways to do that, but I'm going to do it in a way that covers a lot of different models that people might be interested. So we already have Poincare symmetry here. So I'm going to add new generators. So I can do two directions. First, I can make it conformal. If I want to make this, enlarge my Poincare symmetry into conformal symmetry, then I need to add two more new generators, and one is the dilatation generator, D, and the other is the conformal boost, which is alpha alpha dot. Okay, because the conformal boost generator is also a vector generator, similar to similar to translation. Now, actually, so this is also the other thing good about having these on-shell variables, is that there's really little thing you can write down for these generators, so you can basically guess them to begin with. So first of all, let's say we have alpha alpha dot here, and we can guess what this conformal boost generator should look like. It must carry non-trivial alpha alpha dot, right? And we look upstairs, we see that, oh, okay, so we have this lambda and lambda tilde, so that means it has to come from the lambda and lambda tilde, but it cannot be this, because this is already translation. And what the natural thing that you would have here is that you would have simply partial lambda alpha and a partial lambda tilde alpha. So it's the direct opposite of your translation. Okay. Now for dilatation, you know that it is basically anything that has a non-trivial mass dimension is giving you a non-trivial dilatation weight. Then it tells you that since here the only thing that carries mass dimension is this lambda and lambda tilde, and they actually carry 1/2 mass dimension, because lambda and lambda tilde gives you momentum. So this already tells you that the dilatation operator should be lambda alpha partial lambda alpha plus lambda tilde partial lambda tilde alpha dot. Again, I put the particle label here, and then sum over I. Okay? And if you want to see what the algebra looks like, you can just use these generators and just plug it in to do the commutation, and you'll work out what the conformal group actually looks like. The conformal group algebra actually looks like. Okay, so this is one way to generalize. I can generalize to include conformal symmetry. The other thing is to make a supersymmetry, so super Poincare. Okay, now super Poincare needs a little bit more work, because now we have some new generators that are actually fermionic generators. So those who've seen supersymmetry algebra before, you know that we have now superchargers, which I'm going to call Q alpha alpha dot. And the algebra for with the normalization that I'm using, I'm going to use them to be P alpha alpha dot. Okay, so we need to now have something that some new on-shell variables that can reproduce this algebra. Now you already know that here P is written as in terms of lambda and lambda tilde. And you also know that Q, now first of all, Q carries a non-trivial alpha and Q bar carries a non-trivial alpha dot indices. So you already know that you have a feeling that Q should be proportional to lambda or partial lambda. Q bar alpha dot should proportional to lambda tilde alpha dot or partial lambda tilde alpha dot. So that's, we have a good idea. But the fact that these two are fermionic generators tells you that just working with lambda and lambda tilde is no longer sufficient. You need to have something that is fermionic, right? So I'm just going to introduce a new variable and then just dictate that it's fermionic. And I'm claiming that, so I can just have Q alpha equal to sum I, lambda I alpha, and eta I. So now I'm introducing a new variable which is called eta I. Okay, it's fermionic, it's Grassmann odd. And now once I have Q alpha equal to written in this form, this algebra dictates what Q bar must be, right? Because Q bar must be in such a way that actually once I plug it into this anti-commutation relation, I get back P alpha alpha dot, right? So this tells me that with a little bit thought, that this is actually sum over I lambda I tilde partial eta I. Okay? Now, of course, once the derivative hits on the eta, you basically get lambda I alpha and lambda I tilde back, and you indeed get P. Okay? Good. So this means that if I want to have something that satisfies super Poincare symmetry, that means my on-shell variable, now I need to generalize this for super Poincare symmetry. So I'm going to, for anything that is super Poincare invariant, I'm going to change this into curly M. And I'm going to introduce, besides the original angle and square bracket, I need to introduce this new eta variable. Okay, and we're going to spend some time talking about this, what this eta variable means. But let me just first complete my discussion here. Of course, if I have supersymmetry, that means that I can also, once I have one of them, I can have a bunch of them, right? So for extended supersymmetry, extended super Poincare, you basically can just have a bunch of Q alphas and Q bar alpha dots. So you can just put an extra label in here, and then now the algebra becomes delta I, J. And again, all you're having is that this eta has I, and this has an extra I indices. And basically, I runs from 1 to all the way to n, the number of supersymmetry that you can have. Okay, so if you enlarge your group to super Poincare, that means that your scattering amplitude now has to also depend on this extra eta variable. Now, of course, finally, you know what I can do. I can combine these two, and then get what is called a superconformal. Okay, let me just write the full thing, even though you know what I'm. Okay, so I can have superconformal. So for superconformal, we already have the conformal group, we already have the super Poincare symmetry. Then for superconformal, you can actually work out what the remaining generator is just by doing the commutation of these algebras here. And you'll find that you need to introduce what is called the conformal SUSY generators, Q alpha I, S bar alpha dot I, which is basically partial lambda eta I with again sum, and then sum partial lambda tilde I alpha dot partial eta I here. And you also get what is called the R symmetry generators, Raj, which is basically a sum of I, eta I, partial eta J. Okay, so this is basically I start from Poincare. Now in various steps I include new generators. And so if the final function respects any of these symmetry, that means that the final function must be invariant once these generators act on your final function. Okay? Good. So let's look at the now. So for generality now let's look at this function with mn and eta with the inclusion of eta I. So is there?
We keep the.
Oh sure. I'm just gonna push it up. Okay. So let's look at this. So we want. So I've introduced it to yes.
So if I got it correctly, you don't have any lambda, d by d bar, lambda tilde operators in there. Or maybe I missed it.
Yeah, I don't have that. These actually form a closed group. You won't generate that kind of operator by doing commutators of these algebra, of these generators. Okay, so so far the only motivation for introducing this eta now is this eta variable here is because I want to have a super Poincare symmetry. So yes?
Can I not have the R symmetry without introducing super conformal symmetry because it's just the rotation in this I?
Yes, you can have the R symmetry without the super conformal symmetry. There is an issue with what precisely the central charge of this R operator is, and that in principle I can should have a constant there, and what exactly is that central charge? You actually have to fix it using the super conformal algebra. So of course, so everything here they must form a closed group. So once you do the commutator, and that actually fixes the closed form. Yeah, but here just with this this doesn't actually fix what my R chart actually looks like.
And also, when you have multiple supersymmetry generators, don't you have a central charge possibility when you take a Q anti-commute it with another Q instead of a Q bar?
Yeah, so you have that possibility, and then
Gives you any, if you ever get that.
So if I have central charge, then I need to. So basically, here so to be more precise, here the thing that I'm writing down is for the algebra where my central charge is 0. If I actually have non-trivial central charge, for example, if you want to talk about BPS states, for example, if we want to talk about the Higgs, the Coulomb branch of n equals 4 super YAMLs, then the massive particle all have non-trivial central charge, their BPS states, then actually I can no longer use these on-shell variables. But that's expected because then that means that you need to use massive variables. And indeed, for non-trivial central charge, we can work out what the what the on-shell super space formulation is by using now instead of lambda tilde, but the lambda I and the lambda tilde I that I talked about before with the massive spinor helicity. So that becomes depending on and also of course on what the form of your central charge is. Okay. So let's just give a little bit motivation, a little bit more discussion about what is this guy. So what are these etas? Can we have a more physical understanding of what those are? So well, first of all, you already can gather some information by the way how the eta actually starts appearing in your generators. So notice that the eta here appears alongside with lambda. Now I'm using lambda and eta to represent my generator Q. Now of course Q is just some symmetry transformation, right? On the other hand, lambda carries actually a non-trivial little group weight. And more importantly, lambda, having a sum of lambda times eta. Now if I have a sum of lambda times eta, it better be, whenever you have a sum, it better be that all the things in your sum have the same property, right? Since all the little group are actually different, right? As I mentioned, little group is defined particle by particle. So that means if I'm writing this as a sum, it better be that the entire thing is actually, each term in your sum better be little group neutral. Right? Otherwise this makes no sense I'm summing them together. Right? So in order for them to be little group neutral, that already tells you that when I'm writing this, eta actually carries non-trivial little group weight as well. And eta must carry the opposite little group weight of lambda. Okay? So from this you gather that eta must transform as exponential plus a half theta I. Okay, under little group transformation, under my U1. Otherwise, if I write this down, this doesn't make any sense. Okay, just for that formula to make any sense. Okay, good. Now this is extremely important because then this tells me, well, how I should think about my new function here, m of n. So remember, so of course, when I'm writing down my scattering amplitude, in principle, when I'm writing down, this is a Lorentz invariant, but it carries non-trivial little group weight, as we stress over and over again, right? So when I'm writing this curly mn down, in principle, I am actually also labeling all the h1 to hn down. Okay? So I'm going to leave the parentheses. You know that it's a function of these variables. Okay, then in principle, I can do an expansion in terms of how many number of etas I have. So let's choose just eta 1, just without loss of generality. I'm going to expand this function in terms of the number eta 1 I have. Of course, if I just have one, if my supersymmetry is just 1, n equals 1, so I don't have this extra label here, then that means that I can write this in terms of a new function. Let me call this new function m. It's still curly because it still depends on the other guys. So m of n, let me just call this 1, 0th, which means it's 0 power of eta 1. Okay, and times, so it has 0 part of eta 1, and then I write down m of 1, h1, all the way to hn with eta 1. Okay, I'm going to expand this out. Now, of course, here I'm expanding eta 1 out, so that means that here both of these functions, both of these things I've written down with 0 and 1 here, they don't depend on eta 1 anymore. Okay, I've already explicitly written down their eta 1. Now, just by writing this, you'll say that I'm wrong. I cannot do this, right? Why? Because I'm saying that this has helicity h1, and this has helicity h1, but I already know that eta 1 has a plus helicity, plus 1/2 helicity for leg 1. So this doesn't make any sense. The sum of these actually have different helicity weights. So that means that here this cannot be h1, but rather this must be h1 minus 1/2. So that this plus 1/2 can combine with this to give the total to be h1. Right? Everybody agrees? So what does this mean? This means by expanding out in eta 1, I'm actually looking at different helicity components for leg 1. For the 0th component, the leg 1 should have h1 helicity. But for the first component, eta 1, this thing actually has a h1 minus 1/2. Minus 1/2 helicity for leg 1. Okay, so the very fact that I'm introducing this eta here in my symmetry generator in this form, first of all, it tells you that this eta must have non-trivial helicity weight. Furthermore, it also tells you that this function here, in terms of eta, if I expand an eta, it's actually encoding what the different helicity weights I have, the helicity particles I have for each different leg. Right, for here, this is leg 1, I could have expanded leg 2, leg 3, and so on and so forth. Okay? So this should give you the picture that when I'm writing this down, I'm really computing an amplitude where I have a notion that here my external states are no longer just plus 1, minus 1 helicity fields, but rather a superfield, an entire multiplet. Okay? So I'm really computing something with where the total helicity is just h1. And this, depending on which order in eta I'm expanding, this phi of eta is like a superfield where it encodes the different helicity that's being packaged into this entire function here. So so this would be 1 phi eta 2 h2 and phi eta n hn. So in principle, this is really what it means. Okay? And here, what this phi eta means is that there's actually multiple degrees of freedom being packaged into a single super degree of freedom. Or you can say it as a single superfield, even though we don't really have fields in this discussion so far. But this is what is called an on-shell superfield. So for example, if I have some phi h1 eta 1, then this has an expansion in terms of the number of eta. So let's use let's just introduce what's going to come up over and over and again, which is n equals 4. The number of supersymmetry is 4. Then that means I can expand in terms of eta all the way up to 4 powers of eta, because there's 4 different powers. So that means I have some field here, which is phi h1. So let me just call it little phi h1. Then I have the first one. I'm going to phi prime. These I'm going to make a specific identification very soon. h1 times eta. So actually, so I'm not going to put labels here. I'm just going to, this is just for general. It can be any leg. So I'm going to remove the leg labeling just to make my representation compact. So here I have I. So where's my I? Oh, I'm putting upstairs. So I'm going to put upstairs here. Okay, then I got phi prime prime. So this would be I, j, eta j. I'm going to normalize it by half. This is going to by 3/4. And finally, 1. This is just an overall normalization. I'm going to determine what h is very soon. Eta I, eta j, eta k, and eta l. And in principle, I should have I, j, k, l here as well. I'm going to simplify this notation very soon. Okay, so in principle, this means I have all these possible degrees of freedom in my expansion. Now, of course, this is incorrect because if the top field is h, each one of these terms should all be h. But you already know that I, eta has a plus 1/2. So in order to have the correct total helicity weight, this must have helicity minus 1/2. This must have helicity minus 1. This must have helicity minus 2/3. And this must have helicity minus 2. Okay, so once I start with the top helicity h, I determine what are the helicity of all the states that is appearing in my multiplet. Right? So for example, I can start with h equals 0. If I have h equals 0, then I would have the first piece is a spin 0 piece, and all the way to the bottom piece, I have a spin minus 1/2 piece. So this would involve something that has the graviton. 0, yeah, this is minus 2. Yeah, this is minus 2. So this involves a graviton here. This involves a minus 3/2, which is a gravitino here. This has a minus 1, which is a photon field here. Minus 1/2 a spinner and a scalar. You notice if h is equal to 0, then this doesn't form a complete parity multiplet, right? It only has a minus helicity, that it doesn't have the plus helicity. That means that you need to introduce another field here, which has some other h, which here now you can take h equals to 2. If you have something that has h equals to 2, then this completes the entire multiplet. So you have 2 different super multiplets that combine to give you the entire n equals 4. And this will be the multiplet for n equals 4 supergravity. Now for our case, we will want h equals to 1. If h equals to 1, then you notice that here you start from spin 1, and all the way down you get to spin minus 1. So you get the complete multiplet. So a lot of the topics in this lecture series will be about h equals 0. So let me just write it down. H equals to 1. And then I can write down what the explicit fields are. Then you would have a plus 1 gluon here. And then you would have the gluino. There's actually 4 gluinos, which is 1/2 eta I. And then you have 6 scalars. So I'm going to keep this as I and then ij. This is spin 0, so I'm not going to put anything up there. So this is eta I, eta j. And then you have the opposite -1/2, psi bar, -1/2 gluino. Now I'm going to use the other notation, which is I'm going to use here I have eta I, eta j, eta k. And here I'm going to use bar, which has an L here, and I'm going to let it contract with the SU4 little group, SU4R symmetry, Levi-Civita tensor. Okay, and I have a 3 factorial here. And finally, I have the negative helicity gluon. And now I have just basically an eta I, eta j, eta k, eta L. 4 factorial, and everything is just contracted in with the SU4 Levi-Civita. Okay, so this is the n equals 4 super Yang-Mills multiplet. And you can go back and play around with different multiplets, just start putting different fields, different number of n's, and this basically gives you a degree counting of what is necessary to form an entire multiplet. Okay, with various degrees of supersymmetry. Good. So now we have an understanding of what this function actually means when you have these eta here. So let's go back and look at the 3-point, and see what can we write down. That is actually not only, so before we were writing down 3-point amplitudes that respect Poincare symmetry. Now we're going to write down 3-point amplitudes that respect super Poincare symmetry. Okay, good. So now we're going to have look at 3-point again. So now this is a function of angle or square. They cannot be both. And then, but now there should be depend on now eta I as well. Okay. All right. So we're going to try to write something down that satisfies all the symmetry. So of course now we can put in the explicit delta function for the momentum conservation, and let's see what further thing we can write down. Now, first of all, well, because the fact that we have super Poincare symmetry, that means that now the amplitude has to vanish under both of these operators, right? Now again, as I stressed before, whenever you have operators that should vanish on your amplitude, first you want to look at the multiplicative one, because the multiplicative one, which here is P, is Q, the only way it can vanish under amplitude is if your amplitude is proportional to the delta function of that guy. That's the only way it can vanish, right? Because there's no derivative or anything that it doesn't do anything like derivatives or so on and so forth on your amplitude. So the only way it can vanish on your amplitude is if your amplitude is proportional to its delta function. Good, so that tells you that I should write down a delta function for the Q. Now, since my Q is actually a fermionic variable, you know that for a fermionic variable, the delta function is actually itself, right? Because A times A is equal to 0. So keep that in mind. That means that I want to write down a delta function with 2n, where n is the number of supersymmetry I have, with Q. Okay? Now, what does this explicitly mean? So first of all, so let me just write this down. 2nq means basically you just have q to the 2n power of them. Okay, because there's actually n of the q's here, and alpha runs from 1 and 2, so basically the schematic means you have this q and you just have 2n powers of them with all of their indices contracted. So if I write this explicitly out, that just means that I have eta I, eta j, and then I have this as a product of I equals to 1 to n. This is what it actually explicitly means if I want to write everything explicitly out. It's obvious that, oh sorry, I should sum over ij. Okay, it's obviously that your Q, because this is the same Q, and then the Q has a SL2C index here. So that means when I have two of them together, they're going to be anti-symmetric, so you can contract them. So that means that all the spinor indices are actually contracted, and then you just have these eta variables sitting around. Okay, so this is how it actually explicitly looks like. Okay, yes.
Very naive question. Why is eta Grassmann odd?
I needed something that is Grassmann odd so that I can represent this Grassmann odd generator, because the generator is Grassmann odd. If I didn't have this Grassmann odd generator, I don't need the Grassmann odd variable.
But then when you have Q equals like lambda eta,
Yes.
So left-hand side is Grassmann odd.
And this is also Grassmann odd, right? Remember, lambda is a bosonic variable, even though it carries spinor index, but it's a bosonic variable.
Yeah, okay.
Yeah. That's very important. Even though lambda and lambda tilde is a spinor under SL2C, it's not a spinor. It's not a fermionic field variable. Okay, so you already know that just super Poincare symmetry tells you that you need this delta 2Qn, right? Now we need to see if Q bar actually. So what is the constraint of Q bar? Now actually, since you already know that Q acting on Q bar, or the other way around, because this is anti-commutator, so this is symmetric. Q bar acting on Q gives you P, right? So that tells you that once you have this thing, this is already a solution, right? Because this delta 2n is actually just basically just this delta 2n Q is basically just Q itself. And if it's just Q itself, then when Q bar is acting on this function, Q bar acting on Q, you do the anti-commutator, it just generates P. But this P is multiplying by this delta function, this overall momentum conservation, so it's trivially 0. So this, with any function, let me call this f of angle or square bracket, is a solution to the super Poincare symmetry. Yes?
With that logic, only to write on-shell amplitudes, not
Yes.
to write anything off-shell.
Yeah, so we're going to be just thinking about on-shell amplitudes, or on-shell observables here. There's various off-shell variables we can still interpret it as in an on-shell way. For example, you can have correlation functions where you might imagine that it's off-shell, but once you translate it into momentum space, then it's basically a function in momentum space, and then all that it's basically describing is you have momentum which are not equal k squares, p squares not 0, but you can still interpret it as massive, like heavy massive particles. You're talking about some heavy massive particle interactions. And so there's various interesting ways of how to convert what you would usually say an off-shell object into an on-shell language.
Can you just go through how you got that function again? Just the logic.
This one?
No, the f. Just the logic.
Oh, I'm just saying that this M3 is my solution to this M3 is some amplitude that satisfy my my super Poincare symmetry, right? Now the Poincare and the full super Poincare actually already forces you to have this factor here. So this is a solution. So then the only thing you can add on is just some pure function of angle or square bracket.
So why is pure function?
What?
So why is pure function?
Yes, in principle I can have more. Okay, so you're saying that I can have more, but I'm just trying to find a solution to that. So here this is already a solution. I'm not saying that this is a unique, but this is already a solution. So I'm supposed to stop at 12:30. Is that
Yeah.
okay? Okay, so let's just write down some explicit solutions. So again, let's go back to n equals 4. So let's look at what this 3-point amplitude would be dictated by these consider. Oh, actually I have space there, so let me just continue. Good, so you already know. So let's consider n equals 4 super Yang mills. And let's consider the 3-point amplitude. And you'll notice that something is odd. Okay, so for n equals 4 super Yang mills, now again, we had the multiplet. Where's the multiplet? Did I just erase it? Oh, I erased it. No. Okay, I erased it. Okay, if you remember what I erased, you remember that n equals 4 super EMLs, you need the helicity of your entire multiplet, the beginning helicity, to be h equals to 1, right? So it means that it needs to have +1 helicity. Now you already know that n equals 4 super Yang mills, just from this Poincaré's supersymmetry argument, you know that this amplitude should be written as first delta 4 p. Now you have n equals 4, so this is delta 8. Delta 8 q. Okay, where the 8 comes from, the 2 again comes from the fact that you have the alpha index here, which is a SL2C index, so you have 2 component. And then now you have n number of these q's, where this q also carry this I label, and this I runs from 1 to n. So for n equals 4, you have this delta q to the 8th power. If you want to write it explicitly out, it takes this form where I now runs from 1 to 4. Okay, so we know that it must have this form. But you also know that n equals 4 super EMLs has this top multiplet h to be negative, to be +1 helicity, right? So in order for it to be +1 helicity, this function must carry non-trivial helicity weight. But so far, it has no helicity weight, right? So you want to plug it in. So furthermore, since all of the 3 fields since everything is contained in only one multiplet, that means it must be whatever thing that you write down must have the cyclic symmetry in it, because all the fields are the same h equals 1 multiplet. So a natural solution that you will write down is simply, because you remember, so let me first write it down. The natural thing you will write down is just 1, 2, 2, 3, and then 3, 1. Okay? So here, again, you have 1, and lambda 1 has -1/2. You have 2 lambda 1, so this is actually +1 for leg 1, and +1 for leg 2, and +1 for leg 3. Now, why am I using angle and not using square? Can anybody answer? Why am I choosing angle and not square? I could use either, right?
Square would be -1 instead of 1, right?
Yeah, but I can put the square upstairs though, right? I could have put square 1, 2, square 2, 3, and square 3, 1. So is there any reason why I'm actually using angle and not square? Yes?
Did you make an implicit assumption when you wrote down this delta q? Because you've written in terms of the angle bracket.
Exactly. So that's the reason I have angles, right? Because if I'm writing this in this form, then I'm actually implicitly assuming that my angle bracket is non-zero, right? And for 3-point, it has to be either angle equals 0 or square equals 0. Right, you must be either one of them. So when I'm writing this down, I'm already implicitly assuming that my angle is not equal to 0. Right, so that's why I'm writing angle bracket down. But this also points to what something is funny, right? Because if I'm writing this only in terms of angle, then you'll say, what happened to the square equals 0 solution? Right? Shouldn't there be a square equals 0 solution? Right? So this is only one part of my possible amplitude. So this corresponds to what is called the maximal helicity violating amplitude. The reason we call it MHV is if you look at the component, notice that this has delta 8q. So this means that total number of eta is 4. Is 8 of them. There's total number of 8 etas, right? So if you remember, if you just want to look at gluons, 0 number of eta corresponds to a plus helicity gluon, while 4 eta is minus helicity, right? So this has a maximum 2 minus helicity gluons, okay? And usually when we have something that has 2 minus helicity with arbitrary plus, we call this maximum helicity violation amplitude. But you also know that there should be 2 plus helicity gluons as well, what we call MHV bar. So this must be contained somewhere. So you must have something that has 2 plus helicity and only 1 minus helicity. But here you already see that this is delta 8, so this cannot be the possible answer, not to mention that this only gives you solutions where the angle bracket are non-zero. I need to have something where the square bracket is not non-zero. Now, if you want something that the square bracket is non-zero, first of all, you notice that in that case, I don't really need to care about the Q generator anymore, right? Because when I'm writing out the Q generator, you already see that it actually depends on the angle bracket inner product. So if I'm looking at a kinematics where my angle bracket vanishes, actually this Q actually vanishes itself already. So I don't really need to care about that. All I need to worry about is something which vanishes under Q tilde acting on my amplitude. And so I'm just going to write down the solution. The solution is actually now delta 4 p. And in order for me to satisfy that Q bar equation with a little thought, you can see that this is actually the solution. It's actually just written in terms of square. Well, it has to be written in terms of square brackets. I'm going to plus here 3, 1, eta 2. Okay. So first of all, before I continue, let's just take a moment to see why this is a solution. So first of all, this is a delta function, but this is a delta function of my fermionic variable, right? So that means I can just remove this delta function. It's just basically itself. Now second of all, now I act on with my Q bar generator, I act on hitting here, then what will happen? So first of all, each one of these eta is going to hit an eta over here. I should put explicit my index here. So here I runs from 1 to 4, which just explains why there's this 4 factor here. So each time this Q bar acting on my eta, they will replace my eta with lambda tilde 3. With lambda tilde, right? So this is replaced by lambda tilde 3. This is replaced by lambda tilde 1. And this is replaced by lambda tilde 2. So after Q bar acts on it, you get square 1, 2 lambda tilde 3, square 2, 3 lambda tilde 1, and square 3, 1 lambda tilde 2. Does this vanish? It's exactly the Sheldon identity I talked about before, right? So this actually, indeed, it vanishes under my Q bar. So this indeed is a solution, still another solution to my super Poincare symmetry. And the final thing I need to make sure is I need to tie up all my helicity weight counting, right? So here each one, again, eta has plus 1/2 helicity weight. So here everything has plus 1/2 helicity weight in each of these legs. This has a total of 4, so that means this has a total of plus 2 helicity weight for each leg. Now I have too much, right? Because I know that this is supposed to be an amplitude of my n equals 4 multiplet. It should only have plus 1 in each of my leg. So that means you want to divide this thing 1, 2, 2, 3, 3, 1. Okay? So this fixes what the MHV bar amplitude, super amplitude for your n equals 4 super Yang-Mills looks like. But again, you can see that, again, everything is fixed in terms of helicity weights. The helicity weights now, instead of just the particle of your external state, it now becomes what multiplet you have in your external state. Okay, and basically the helicity weight and super Poincare symmetry tells you that there's these two solutions, and basically that's the only solutions that you can basically write down. Do I need to stop?
Is that a reasonable spot?
Yeah. So basically we finished all the 3-point amplitude discussion in terms of using and I've already introduced all the on-shell variables, and so I think this is a good place to stop. And for the afternoon section, we should get past 3-point, right? So we're just gonna jump ahead and start looking at what constraints we start to have at 4 points and beyond, and give general discussion with general endpoint tree amplitude. So tree amplitude will be the focus of today's lecture. Okay. All right. Thank you.
Thanks a lot, Yutin. Are
Okay.
there any